So, let us come to our 29th lecture on this transport phenomena. Let us come to TP 29, in which we will study the insulation, and we will try to understand the critical thickness of insulation. These are the two topics which will be covered in the class. Critical thickness of insulation. These insulations must have a lower thermal conductivity value. Its purposes are, its purpose is to prevent the heat loss or heat flow, is to prevent heat flow from the system to surroundings and vice versa. These are used in where these insulations are used in air conditioners, boilers and steam pipes. These insulators are also used in the refrigeration and the food processing industries, refrigerators and food processing equipments. Because of the fact that these insulators constitute an important class of material, and also I have said you that these insulators have a lower K value, that is a lower thermal conductivity value. Henceforth, it is quite reasonable to state that you must have enough understanding of all the factors which can affect the K value of a material. So, factors affecting the K value. This is very important, that what are the factors which can alter the value of the thermal conductivity. Those factors are number one, temperature. We will discuss these factors one by one. Number one is the temperature, second one is the density, number three, direction of heat flow, specific heat, etc. These are the four important factors on which the value of thermal conductivity depends. And also, apart from all these things, apart from these factors, pressure is also responsible for altering the K value to some extent. K value for some extent. Because of the fact that this can alter the K value, pressure can alter the K value by a very small margin. So, that is why this point is supposed to be non-important point, but we will discuss this as well. Now, coming to the temperature, thermal conductivity is a function of temperature. Given as K is equal to K0 into 1 plus alpha Tm. Because Tm varies over a range of temperature, so it is important to visualize a concept of mean temperature, which have been given here as alpha into Tm, that Tm is the mean temperature, and K0 is the value of the thermal conductivity at 0 degree centigrade temperature. So, the K0 is equal to K0 into 1 plus alpha Tm, or better to say alpha T. It implies that if you increase the temperature, it means the thermal conductivity will also get increased. Now, taking T is equal to Tm, that is mean temperature. So, we can write K is equal to Km, that is equal to K0 into 1 plus alpha Tm. The question arises how this mean temperature Tm can be evaluated. So, Tm can be evaluated as this Tm can be evaluated as Tm is equal to half into T1 plus T2, that is the maximum and the minimum temperature. However, if K is equal to K0 into Ft, definitely this is also a Ft with the insertion of alpha, that is the coefficient of linear expansion. Let us suppose K is equal to K0 into alpha T, then the value of Km is evaluated as 1 upon T1 minus T2, if T1 is greater than T2, T1 minus T2, integration from T2 to T1, Ft dt. This is the technique for the evaluation of the mean thermal conductivity value. An expression for arriving at mean thermal conductivity value. Second factor is the density. So far as the effect of density is concerned, there is no clear-cut guideline are there. So far as the effect of density on the thermal conductivity is concerned, no clear-cut guidelines are there to make a conclusion that whether particular density will give the maximum thermal conductivity or not. However, in the case of some of the powdery and some of the fibrous materials, there is a value of density at which that material has a lowest value of thermal conductivity. So, regarding the density, no clear guidelines are there, but for some powdery and fibrous materials, a minimum thermal conductivity value is there at a particular density. The variation of density, the variation of thermal conductivity as a function of density can be expressed diagrammatically as in the by means of a graph. It can be represented as here along the y-axis if you take the value of thermal conductivity watt per meter degree centigrade, and here along the x-axis if you are plotting density kilogram per meter cube, you will find that, let us suppose this is for fibrous materials, and this is for powdery materials. You will find that both has a minima, and this minimum value of thermal conductivity corresponds to a given value of rho for the powdery materials, whereas in the case of materials as well, you will find a minimum value of thermal conductivity corresponding to a particular density value for the fibrous materials. So, this effect of density in the case of some of the fibrous and some of the powdery materials can be treated as these guidelines, for which the data are available in the standard handbooks of the heat transfer. Coming back to the third one, that is the direction of heat flow. The third one is the direction of heat flow. Third one is the direction of heat flow. Direction of heat flow determines the K value in materials, example wood, K in the direction, K in the thermal conductivity in the direction parallel to the heat flow, direction parallel to heat flow has 60 to 80% more value as compared to that along a direction to the heat flow. You may ask me that what is the important thing that can be concluded from here? The important thing which can be concluded from here is whenever and wherever you have to design a fire resistant board from the wood, it is necessary to keep the fiber direction perpendicular to heat flow. This is one of the most important design factors so far as the design of the fire boards are concerned. So, it concludes the matter that while designing the fire boards, it is necessary to keep the fiber direction perpendicular to heat flow direction. The next one is the specific heat. So, next one is the specific heat. So, the fourth factor is the specific heat. Fourth factor is the specific heat. Experimentally, especially the engineer named Austin, who have conducted so many experimentations regarding the establishing a relationship between specific heat capacity at constant and the thermal conductivity of many amorphous materials. So, during the experimentations, what Austin found experimentally that it is found that the rate of heat flow Q is directly proportional to the change in the internal energy with respect to the distance. So, this is a relationship which has been developed by Austin, a mechanical engineer by profession, Austin. So, it can be written as Q is directly proportional to dE upon dt into dt upon dx, same. Now, this dE by dt, this quantity is called the specific heat capacity at constant volume. So, Q is directly proportional to Cv into dt upon dx, okay, as Cv is equal to day by E by day by T at constant volume. From thermodynamics we know this is the value of Cv. So, Q varies as Cv into dt upon dx. If the temperature gradient dt by dx is constant, if this is treated as constant, then the Q, that is the rate of heat flow, is directly proportional to Cv, and also if dt upon dx that is equal to 1, that if I am considering the unit temperature gradient, Then according to the Fourier law of heat conduction, as I have stated you already in the most in the introduction class to the heat transfer, as well as in the many circumstances, that if you are using the unit temperature gradient, then the quantity of heat flow per unit area under the unit temperature gradient per unit time is what is known as thermal conductivity. Then if dT upon dx is equal to 1, then Q is equal to K. Now Q is varies Cv and Q is equal to K. If dT upon dx is equal to 1, it means there must be some relationship existing between Cv and K. It means there is a relationship between Cv and K. As an example, in the case of amorphous materials, in case of amorphous materials such as metallic glass, in case of amorphous materials, the value of Cv by K is equal to a constant for a wide range of temperature. It means Cv can influence, that is the specific heat at constant volume can influence the thermal conductivity value. Apart from these four factors, the pressure has also some effect on the thermal conductivity value. So the effect of pressure, however, this effect is not so much pronounced. If you decrease the pressure, atmospheric pressure, then the value of thermal conductivity also decreases by some margin. So these are the factors on which the thermal conductivity depends. So the next topic of our discussion today is the critical thickness of insulation. So coming to, prior to that, first, what are the requirements in the insulators? What are the necessary requirements which must be there in an insulator? Desirable properties in insulators. What are the desirable properties? Number one, it should be light in weight. And the second one is it must be fire resistant in nature. So these are the two requirements which needs to be there in order to design the insulator for a particular industrial equipment. So let us come to the second topic of today, that is the critical thickness of insulation. Now come to the next topic of today, that is the critical thickness of insulation. insulation retards the heat flow, the statement cannot be taken granted, always. Why it is so? That taking the case of a spherical for a cylindrical system, if a hollow cylinder is let us suppose cylinder is there, the internal radius is r1 and the external radius is r2. Let us suppose you are putting some insulation over there, then the quantity of heat conducted that needs to be dissipated through the convective medium, through the convective heat flow mode, which is a direct function of the area. Both the conductive and the convective heat transfer both depends upon the area. Later on, when we will take the specific example of the cylindrical system as well as put some special reference to the spherical systems as well, you will find that the thickness of insulation depends a lot and its effect depends a lot on the radii of the cylinder or sphere. If the critical value is lesser than the outer diameter, then it has some other effect. If the critical thickness of insulation is more than the outer diameter of the cylinder sphere, it has some other effect. That is why I am saying that every time the insulation retards the heat flow, this matter cannot be taken granted all the time. So, addition of a small amount of insulation over a small diameter wire tube leads to an increase in heat flow rate to the ambient air. It derives into the fact that there must be a critical thickness of insulation. There must be a critical thickness of insulation, and that is why it is necessary to go into the mathematics in the critical radius of insulation. The concept may be elucidated by taking an example of cylindrical systems as shown in the figure. What is that cylindrical system? Let us suppose this is the inner radii, R1, this is the thickness, let it be the outer radii, let it be R2, let it be R2. This surface is at temperature T1 and this surface pertaining to this R2, this is exposed to the atmosphere. So, TA, let us suppose this is the ambient air temperature, and this, let us suppose this is the insulation thickness. Let us suppose this is the insulation thickness, etc. So, if I would like to propose an electrical circuit for the present case, how it looks? It looks as this is the T1 temperature. This T1 temperature, the heat energy needs to flow through this insulator. This is the insulation thickness. So, this is the R insulation. Now, it will come in contact with air. So, this is the convective resistance, that is the RA, and finally, the ambient air temperature, equilibrium ambient air temperature will be arrived. So, this is the circuit, analogous electrical circuit for the present case. Now, let us try to extract the value of the critical radius of insulation in this cylindrical system. So, this figure is the solid cylinder of dia 2R1, and this is the equivalent electrical circuit. This is your equivalent electrical circuit. Let us try to start the derivation from this diagram itself. So, since this is the cylindrical system, so applying the Fourier equation, we have determined the heat flow rate in these cases, and that can be given as as per the electrical analogous for the present case, we can write that the total resistance that the heat energy will face, that is R total, that should be equal to R insulation plus resistance offered by the air. So, RA, that R insulation, that should be equal to ln R2 upon R1 divided by 2 pi K2L, because K2, K is the thermal conductivity of insulation, because this is pertaining to the R2 diameter, that is why I have written the K2 here. So, this will be the insulation resistance plus 1 upon the convective resistance, which is equal to 1 upon 2 pi L H naught into R2, that is H naught into A. So, thus the heat flow rate, thus Q, that will be equal to temperature difference divided by total resistance. The temperature difference was T1 minus Ta divided by this total resistance, that is equal to 1 upon 2 pi L 1 by K2 log E R2 upon R1 plus 1 upon H naught R2, right. So, I have to remove this now. The work is over for the present case. Let it be question number 1, let it be question number 2. Now, question number 2 as R2 increases, what will happen? If R2 increases, then this factor will increase, but at the very same time this factor will start to decrease. So, this factor 1 by K2 log E R2 by R1, this will increase, but 1 by H naught R2 will decrease, and that is why there is a concept of critical thickness of insulation. So, thus it implies that is equal to Q max if when Q will get maximized, this Q will be get maximized if this numerator in the equation number 2 will get a minimum value. If numerator in the equation number 2 has a minimum value, has a minimum value. So, Q is equal to Q max if the numerator in the equation number 2 has a minimum value. For minimum value to happen, so for minimum value to happen, what is the requirement? The requirement is, it means d by dr2, because r2 is a variable, into this quantity, 1 by 2 pi L 1 by K2 ln R2 upon R1 plus 1 upon H naught R2, that should be equal to 0. Keeping this is a constant quantity, so we can write d upon dr2 into 1 upon K2 ln R2 by R1 plus 1 upon H naught R2, that should be equal to 0, or you can further write or 1 upon K2, the differential coefficient of this will be R1 upon R2 into 1 upon R1, okay, minus 1 upon H naught R2 square, that should be equal to 0, or 1 by K2 into 1 upon R2, that should be equal to 1 upon H naught R2 square. So, the value of R2, is equal to K2 upon H naught. K2 upon H naught. Let it be question number 3. Now, taking the second derivative, that means d by dr2 of this quantity 1 by K2 into 1 upon R2 minus 1 upon H naught R2 square at the value R2 is equal to K2 upon H naught. You have to evaluate this. That will come as first I have to differentiate this 1 by K2 into 1 by R2 square minus plus 2 divided by H naught R2 cube. The value of R2 is equal to K2 upon H naught. That will be arrive as 1 by K2 into this minus 1 by R2 square so that will be value of is there any mistakes 1 by K2 R2 this okay. Okay, that is equal to minus 1 upon K2 into R2 has a value K2 upon H naught. So 1 by R2 is equal to H naught square by K2 square plus 2 upon H naught into 1 by R2 cube, that means H naught cube divided by K2 cube is equal to minus H naught square by K2 cube plus 2 H naught square divided by K2 cube, that is equal to H naught square by K2 cube. This quantity, see this quantity H2 divided by K2 cube, which is always greater than 0, it can never be lesser than 0. It is always greater than 0. It means R2 is equal to K2 upon H naught. The numerator Q, the denominator has the minimum value. This R2 value is called critical radius of insulation, that is R2 critical, that is equal to K2 upon H naught. K2 upon H naught. And similarly, for the R2 critical value for a sphere, you derive yourself that is equal to 2k2 upon H naught. Hence, the expression for the critical thickness, hence expression for the critical thickness that is equal to R2C minus R2. This is the value of the critical thickness of insulation. Now, if you plot a diagram between the Q value and the R2 value, you will find a curve like this. This means these are the maxima at this point, and this point will correspond to R2 is equal to R2 critical. So, if R2 value is lesser than R2 critical value, then the heat flow rate will increase by increasing the insulation thickness. But if R2 is greater than R2C, it means heat flow rate will get decreased. If insulation thickness increases. So, this defines the concept of critical thickness of insulation, which is of immense importance so far as the practical application of the insulation in the case of heat pipe, in the case of steam pipe, in the case of pipes which is carrying out the water at a higher temperature. In all those cases, this critical thickness of insulation is of immense importance. In the next class, we will go through the heat transfer analysis of the rectangular fin, their special cases. Thank you.